Let's now see how we prepare alkynes. One method for preparation of alkynes involves acetylide, which we use to prepare more complex alkynes from simpler ones. So this would be an example of an SN2 reaction with a suitable substrate, which gives us this internal alkyne starting from the original terminal. This reaction is subject to the same conditions that any other SN2 reaction is. So if you take this iodide and treat it with sodium acetylide, we will get alkyne substitution. We can also do the same with phenylacetylene, sodium amide. And the substitution in this case will give us this hexynyl benzene, and the yield here is about 80%. But all of these two reactions work quite well. Acetylides are also strong bases, so one must consider that when we talk about their preparation, because if we try this reaction, then what we'll most likely get is an E2 reaction rather than SN2. And we'll get back our starting acetylene and an alkene at the end. So that's not very useful. Now acetylides, because they're so nucleophilic, can also react with carbonyl compounds. And so we can have this reaction, which then expels this and moves it to oxygen. So overall we get R1 and R2 and O minus, and this finally gets protonated to give us an OH group here, and it looks like this. And this is a very useful reaction because starting with formaldehyde, our R1 and R2 groups with hydrogen, so we'll go to primary alcohols. Then starting with aldehydes, where one of our R groups is an actual substituent, we'll go to the secondary hydrogens. And then starting with ketones, where both of our groups are R's, we'll get tertiary alcohols. So just simply by varying the nature of our starting material, we can get all sorts of alcohols, which expands our synthetic arsenal greatly. Here is an example of this one reaction that does that. So we start with the cyclohexanone, which is a ketone. We treat that with sodium acetylide, and we'll get this ethynyl alcohol, which upon protonation gives us the final product. This. But if you think about this, all of these reactions that I've shown you, they are a little bit derivative because we start with one alkyne and then at the end we get another alkyne. But the question is, how do we introduce that original triple bond in an organic molecule? And the answer to that is that we really do an elimination. We introduce pretty much the same way we do with alkenes. So we've seen with alkenes that if we have hydrogen and say some leaving group on adjacent carbons, then under influence of base we can eliminate those two groups and get to an alkene. With acetylene, to get to an acetylene, we need to start with a compound which eliminates two AHX substitutions. So either these two, so this will be vicinal dihalide, and if you eliminate two AHX molecules, we will eventually get to the alkyne. Alternatively, we can have both X substituents be on the same carbon. This will be a geminal dihalide. And elimination in this case would, the first case, would give us the same compound. This would be this vinyl halide, which then eliminates again to give us an alkyne. Now, the first step proceeds pretty much exactly the same way as we've seen in the preparation of alkenes. But the second step eliminates from an sp2 carbon. And I've told you in previous lectures that this is unusual, that it requires rather forcing conditions. So this base has to be very strong to achieve this otherwise unfavorable transformation. And so the things that are typically used are molten KOH, so very aggressive reagent, or sodium amide. And so once we do that, such as in this example, we'll be able to eliminate this dibromide with KOH at 200 degrees centigrade to give us an alkyne in about 45% here. Yeah? So this reaction works quite well, and typically these dibromides are made from alkenes because the alkenes can be brominated, and that introduces two bromine substituents into adjacent positions on double bond, giving us precursors to double dehydrohydrogenation to give us an alkyne. However, there is a risky element here, and that is that under these highly basic conditions, there is a possibility of rearrangement. And I'll illustrate this mechanistically here. Now, under the influence of a very strong base, we can deprotonate actually carbon right next to an alkyne triple bond to get to a species which has an anion here. And this is now a resonance stabilized anion because we can push these electrons over here and get something that looks like this. And now this compound can be abstract back that proton from the base to give us an organic molecule we've seen already, which is known as an allene. If this allene reacts with the base again, we'll get back to the same thing, but we don't necessarily have to do that. The allene can react with the base again to eliminate the other proton, which in this case will give us this thing. And now this again is resonance stabilized. Anion with these two structures. Finally, this anion can now react back with the base, take back its proton to finally give us an alkyne that looks like this. And what we see now is that the triple bond migrated which is an important and often problematic element of this reaction. We can have a base-induced migration of a triple bond. Now, in case of terminal alkynes, this can actually be beneficial because if we get a terminal alkyne, we'll deprotonate it and then get the satellite, which is effectively removed from the equilibrium. So then this is not such much big of a problem. So basically, to finish this subtopic in today's lecture, alkynes can be prepared in two main ways. The first one, and the fundamentally more important one, is the double dehydrogenation, which eliminates two HX molecules from a molecule of double alkyl halide, which can be either vicinal or geminal alkyl halide. Alternatively, alkynes can be made more complex by reaction of acetylide anions with either carbonyl compounds or alkyl halides to introduce more complexity into the molecule while maintaining the triple bond. This will be all for today. In next lecture, we'll see how alkynes react and how the reactions are similar, but also at some facets a little different from the reaction of corresponding alkenes.